So yes, this is the one of the grand challenges.
Yeah, great. Yeah. Leave it to.
Okay, so it's time is now is ready. So should we start? Okay. So our next speaker is Professor Chandrajit and how to pronounce her last name? It's
Bajaj.
Bajaj. Okay, very nice. Okay, thank you. So the title is already displayed here. So I maybe you just start. Okay, so let's welcome.
Yeah.
Okay, yeah.
Thank you very much, and thanks to the organizers for inviting me. These COVID years, we stopped to meet with each other, and that is one of the things I miss most, is to interact with everyone. So yeah, the title is long. It's Learning Optimal Control. It also talks about stochastic models and Hamiltonian dynamics. And then finally, the connection to geometry, which is shape and function optimization. So I will try to lead you through this. I should mention this is together with my PhD student, Minh Nguyen, who's extremely bright student. And if you're looking for postdocs or faculty positions, he's going to be a big catch. So the funding, we have support from NIH, NSF, and it's customary also from the Army Futures Command and the Peter O'Donnell Foundation, which funds our institute. So what is shape optimization or shape and function optimization? So a general formulation can be given as follows. Suppose that we are given a collection of subsets omega of Rd in d dimensions. And L is this collection. It's the collection of all possible admissible shapes that we are going to search over to find the optimal shape. For any bounded subset, this can be the collection of all open subsets of D as well, because some shapes we are interested in the interior and not so much with respect to their boundaries. There's also two functionals that are given, which are the objective of the optimization. One is the cost functional, and the other is a constraint functional. So the problem is to find the optimal shape, omega star, given any initial state, omega from your collection, and you're trying to find that optimal shape that minimizes this functional f, the cost functional, and then also subject to the constraint functional. So it's a constrained optimization problem involving these f and g's. By the way, I know it's difficult in online, but if there's a question, just call out and say, excuse me, and that's a better way to interact. And so don't be silent. Okay. So the classes of shape and function optimization, as you all perhaps well know, is a problem as soon as geometry was applied. People want to get the best geometry, the best shape, the best design so that you can satisfy all the constraints. And so this is a very large topic, but we broke it up into two classes. The first class is, defines the two functionals, f and g, directly in terms of the shape, omega. And a famous example is the isoparametric problem, which I will go into some detail today. And the second class is that the two functionals are defined indirectly. So you start with the domain omega, you solve some partial differential equation, which is of some function on that, and then your f and g functionals are functionals of this u of omega. And examples of this are the minimum mean compliance or optimal interfaces. Kay was asking me about proteins. And so this is, what is the optimal interface between a protein's interior and the solvent where it lives in? Of course, there's this challenging lowest eigenfrequency maximization problem. So what is the isoparametric shape optimization problem? It says, among all open subsets omega of Rn, find the shape omega with the minimum parameter given a fixed volume. You can think of this shape, omega is omega star. In this problem, the volume function is just, the fact that it's a fixed volume is a constraint functional, and the parameter is the functional that you're trying to optimize. And so you can set it up as a quotient problem. So you can define your functional f of s, which is the parameter of s. It's directly a functional of the shape and the square root of the area. Of course, this will be volume in higher dimensions. So this is an example in 2D. And as you were perhaps noticing, there was a little video here showing how from an initial shape, you actually reach the final shape. So you started off with this square shape and you reached a shape which optimized S. And so, of course, the optimal shape should have constant positive curvature. If not, you can always improve the isoparametric inequality or the objective function. What about the minimum shape compliance optimization problem? This is much more complicated. It's saying, I give you a material domain on my omega, and there's, various loads and body forces. I'm trying to find the shape which minimizes some functional called the elastic energy that depends on both the domain omega and, of course, u, which is the constraint, which is part of your partial differential equation. Here, this is presented in a weak form, but this is your full 3D elasticity problem, which, as we all know, is a complicated problem. Even with linearized strain tensors, the elasticity tensor is anisotropic and quite complicated to solve. And imagine you're trying to optimize this subject to all these constraints, and so your Lagrangian, if you're doing it in augmented Lagrangian methods for constrained optimization, is very, very complicated. Notice also that in the shape, topological changes occur. So it's not only the geometry is being modified, the topology also will modify. And there are notions, as we'll talk about, of geometric derivatives and also topological derivatives as these shapes are changing. So in the rest of my talk, given this introduction, which is brief, I want to focus on the exact thing that caused us to study this, and saying, if you put this in a general machine learning framework or a general reinforcement learning framework, how do we solve this in a learned fashion? So the shape optimization problem is difficult because we're minimizing over the set of all possible shapes in a collection instead of just variables in some RD. And it's also well known that these problems are analytically somewhat intractable. Nice reference in a book by Bucher and Buthaso. So my aim in this talk is kind of twofold. I want to develop a new general reinforcement learning approach and a framework that can work with almost all shape optimization problems in these two classes. So it's a great challenge. And today I'm going to show you some of the progress we made and the results we obtained. The environment in this reinforcement learning framework needs to be accurately learned. So not only are you looking at the shape, you're looking at the environment the shape is in. And that makes the state space to be, doubly or maybe triply exponential. So not only is the shape space problem in infinite dimensional space, the environment itself is much, much, much bigger. It's like trying to learn how to swim, and you're trying to control yourself, but you're swimming in not only your swimming pool, but you're supposed to train so that you can swim in the ocean. And so the environmental conditions are what will impact you greatly. So in the rest of this talk, I will discuss this isoparametric problem, since this is an applied geometry conference, and also show you how we developed this new stochastic reinforcement learning, which are tied to optimal control, based on a learned Hamiltonian dynamics. So just as a quick overview, what is reinforcement learning? And so I feel I should mention that because what we are developing is a new technique other than prior techniques. But there's a lot of work in the last 15 years on reinforcement learning. In reinforcement learning, we train an agent interacting with the environment to learn the best sequence of actions to take. The notion of an agent, of course, is a machine learned program, but the interaction with the environments are crucial. And the agent chooses actions, so it's like a dynamical process, a decision process, according to its policy. And the policy is parameterized by some theta. Given the current state, it tells you, based on this policy, what action to take when you're at state ST. And then every time you take an action, the environment produces a reward and you transition to the next state. And this transition is governed by a stochastic transition function. It's the probability of you going here because after all, you're making a decision and there are choices. And which choice is the best choice to make locally so that globally you can maximize the total cumulative reward. So the goal of the agent is to make local decisions such that it can eventually maximize the expected reward that it will receive. So classic problems, and they're nice frameworks that people study, is this cart pole problem and the mountain car problem. Developing any new theory or new method, it's always good to see, does it work well for the simple cases? And you can think of this also as a shape optimization problem. The cart pole problem is, can you keep the shape of the pole and the cart balanced such that with gravity it doesn't fall down? And so this is, you learn how to balance the pole. And here in the mountain car problem, you learn from scratch by exploring the mountain and also learning how to apply the right forces so that you will make yourself on top of the mountain. So both these problems, I'll show you some more details about it. Continuing on this overview, I'll keep conscious of time. There are several methods, and I've picked just a few in reinforcement learning that people have developed in the last, like I said, decade and a half or more. In agent training, you're basically trying to optimize your policy, your action policy, to give you the optimal reward in all of your decision making. And naturally, policy gradient methods, which is based on differential programming, are methods that parameterize this policy and update its parameters so as to maximize its objective through backward stochastic gradient methods and others. The problem is, of course, of what is the choice of metric to evaluate the closeness between the current policy and the update policy so that you can apply these derivatives. And these derivatives are over policy spaces. So depending on your representation of the policy, the appropriate metric has to be chosen on that policy space. And just Euclidean distances often lead to poor results. So what people have developed are, looking at distributions on your policy space, and hence they use the Kullback-Leibler divergence. And in natural gradient methods, of course, this is approximated by the Fisher information matrix. And the gradient of this Fisher, in this approximation is often used in methods like TRPO, trusted region policy optimization, and proximal policy optimization. References are here. Another very rich class of problems is what are called, in reinforcement learning, are called actor-critic methods. Here you learn both the policy function and the value function. The value function comes from the critic. It's like working together with a teacher. So while the actor is the agent that's learning, the teacher is also learning how to evaluate you so that it can guide you to giving you the best policy that the actor can learn. And so this is expressed in this functional where the gradient of the policy now has this psi t term, besides taking the sum of logs of the of the policy function. And here you have to update both the parameter of the actor based on the evaluation from previous rounds. And then, of course, the value is also updated as you go along. So both the policy and the value functions are trained by two neural networks called the policy network and the value network. The second thing I want to talk about, of course, is there's a lot of work that has been done, but a brief summary is prior work on shape optimization and using reinforcement learning. The two main ones are Lambton. They optimize the shape of airfoils based on computational fluid dynamics models of the environment. And this computational fluid dynamics model is, of course, solving Navier-Stokes equation. And so you are using and leveraging all the numerical solution methods. So you assume it's a black box that you can query every time you change the shape. You can go back and obtain the new velocity field and the new pressure field. So this is, of course, requiring supercomputer calculations as well. But the reward is then, find the optimal shape such that the airfoil's lift coefficient are, based on, of course, the shape changes that are allowed. The shape changes are captured by parameterization like the thickness and camber. And camber is like this relative asymmetry between the top part of the shape of the airfoil and the bottom part of the shape. So another very nice paper, which came out just a few years ago, was by Vikara and co-authors. And they also work with the CFD domain. The environment is a CFD model. The learning exercise is, however, simplified and consists of a single time step. The actions they take, the output of the policy network, and the reward they construct is based on lift to drag ratio. So not just the lift in the design. And this work uses the PPO algorithm that I referred to earlier. Both methods, for the domain that they work on show very good results. And hence, but the big assumption is they have to have this giant Navier-Stokes solver in the background that can accurately give how the shape interacts with it. Very much like what I was mentioning to Kay just before we started. The biggest challenge is interaction with the environment if you're trying to define optimal interfaces. Now, there's a big connection, of course, which was well known even back in '71 in David Kirk's wonderful book on optimal control theory of how you learn optimal control, and it's similar to reinforcement learning. So Todorov, of course, from the University of Washington, has written much about this, as has several other people. But the process of control, of course, is that you have a forward process and you have to have some feedback where the controller keeps governing and monitoring the trajectories that you take. Of course, some of these trajectories have to be integrated. So these are path integral methods. And so one of our big challenges is and I'll show you, is we'll simplify this entire thing using a very nice thing called the Pontryagin maximum principle. But learning optimal control models for unknown dynamical systems, where I'm not given the full Navier-Stokes, is key, because most of the time you don't know the interaction of your shape with the environment because the environment is too big to capture. And any approximation of the environment will not capture all the variables. It's just an approximation. So what one needs is a method of controlling by also learning the unknown dynamical. And of course, you're saying, oh, that's like a double problem. But the answer is yes, you have to. But the difference is that you don't have to learn the best model for the environment. You have to learn the model which is exactly customized for your problem and your shape. Now, learning optimal control solutions, is this objective cost functional is optimized over space-time state action sequences with the environment. Reinforcement learning is similar. You're convergently learning an optimal state action policy actioning on optimal value paths with maximum reward or minimum regret, right? So it's either a maximization problem or minimizing the regret function. And of course, you need stable numerical solution techniques because these are very high dimensional and high variance constrained optimization problems. And of course, several people have shown this connection and have applied optimal control theory to guided search in reinforcement learning. I'd recommend these two references as you want to go deeper. So what is our approach? We call it NeuralPMP for, of course, the Pontryagin maximum principle. We're going to learn optimal control solution models with Hamiltonian dynamical systems and apply the Pontryagin maximum principle to build the control into an adjoint state, which is then governed by the generalized Hamiltonian dynamics. So we rely on both the physical nature of the unknown dynamical system and the necessary requirements of the optimal control sequence or trajectories subjected to these physical dynamics. We will learn a reduced Hamiltonian dynamics and learn to optimally control this dynamical system for targeted objectives. So we'll use the Pontryagin maximum principle to reduce this optimal control reinforcement learning problem to the data-specific form of Hamiltonian dynamics. And then the control is going to be encoded into an adjoint variable, and this generalized state and adjoint variable or state and co-state is then learned together. So hence, if you remember the control process picture I showed you earlier, it's simplified into just a forward dynamics learning. You don't have to go back into this feedback loop where you're learning the controller and you're learning the dynamical system. You kind of put them together, and the magic happens by the giants who've thought about this earlier, and we are just using it now. So learning optimal control, aka reinforcement learning, we start with the generic formulation of the optimal control optimization within first a finite horizon. So assume you have a state in a state space and a control in a control space. And what you need to determine is an optimal control action path or policy, which is always a path that lies within your control space. And the cost for that control has to be minimized. So you're minimizing this regret functional, as people say in reinforcement learning, which is the functional which involves this integral, because the cost is not known of the path you take until you reach the final end. And the final end cost is how far were you from the true solution is captured in this terminal cost function. So this first term is the running cost to move along a control path. And if you were to solve it like people have done in reinforcement learning discretely, you're making local decisions along the path, and you're trying to find the optimal way to, say, climb up that mountain for that mountain car. Of course, in a more than a one-dimensional curve, you might not land at the perfect spot that you want. So you have a terminal cost of saying, oh, you are almost there, but try to optimize some more. So the terminal cost is also an important figure or term. So to simplify this, you can think of the optimal control problem is learning this optimal path, the optimal control path with the least cost, because the functional is a least cost functional plus the terminal. But of course, the way you move is subjected to the dynamics. You can't just move arbitrarily. If you are a object in water or a protein in solvent, you are subjugated to the dynamics is controlled by the interactions with the environment. If you are just a pole and the environment interactions of the air are minimal, it's not a stormy, balancing a pole in a very quiet environment is different to balancing a pole in when the winds are blowing. But you can learn both because that's all captured in this unknown F, which is guiding you how you can move. So this dynamical constraint functional is important. Now, a straightforward application of dynamic programming, where, which is one of the solution ways in which reinforcement learning and the Hamilton-Jacobi-Bellman equations were produced, is to basically look at this path integral minimization. And you can do this for stochastic as well, based on your variables being, and your transition functions being stochastic. So the cost to move is a stochastic function. And the problem here is that if you're trying to, apply the straightforward algorithm using something like a deep Q network or doing discrete time, this integral will kill you, because you can't keep, how you adaptively sample this integral for the accuracy is based on the objective of this cost functional. And the number of times you make this discretization, you have to make a decision of choosing the correct based on a policy. So there's too many decisions to make as you go along. And, while you're searching for the right path to take, it's like too many steps. And at every time you have a choice of which steps to take. So imagine you have this climb to, say, Shandao in China, and you have to, climb maybe 1,000 steps, but it's not 1,000 steps, but 1,000. It's a complete graph. You have many choices of going along many steps, and you're trying to find the optimal way to go up without knowing the steps to begin with, because that's the part of the state space is so large, you can't just first build a map of the entire state space. So this is what motivated us to do two things: to use the Pontryagin maximum principle, as well as formulate an algorithmic solution for continuous time reinforcement learning and not just discrete time. So to do that, one has to rely on Hamiltonian systems. So what's a Hamiltonian system? A Hamiltonian system is like an energy that governs, it's like the total free energy of a molecule that governs how the molecule moves. And so if X is a state space, Y it's dual, then we can take bounded subsets of X and Y, V be the control space. Then the Hamiltonian that governs is this inner product of P and this unknown F, and of course your cost functional LQV, the cost of moving. And so this Hamiltonian governs the entire motion under control, right? So the Pontryagin maximum principle provides a necessary condition for the optimal solution of this Hamiltonian. So the control is now built into the energy function that you're trying to optimize. And so this is the famous principle in optimal control theory called the Pontryagin principle, in short PMP, which is the theorem that if QV is the optimal solution to the control problem, which is minimizing this cost functional, then there exists an adjoint variable, P dot of Q, Q being your original state. There's this adjoint state, and the optimal solution is just a solution of this now coupled symplectic dynamical system. The dynamical system is Q dot T, is governed by the pth derivative of the Hamiltonian, and the P dot T is governed by the negative of the qth derivative of the Hamiltonian. Of course, subject to these initial constraints that PT is exactly equal to the gradient of your cost, your terminal cost. So the adjoint state is really governed by the gradient space or the tangent space. And furthermore, of course, over all possible controls, this is a minimizer. So to be optimal, you have to be, your control path V must be a minimizer of your Hamiltonian. So what we developed then is using this theory, which I'm giving you just a simple version of. We developed a two-phase deep learning architecture called NeuralPMP. So in the first phase, we learn a correct reduced Hamiltonian of the controlled Hamiltonian dynamics obtained by application of the PMP to the original control problem based on the unknown dynamics and also the cost functional that you're imposing. And then the reduced Hamiltonian deep network can be trained by going backwards in time from minimizing a loss function deduced from the Pontryagin principle. And I'll show you this a little bit more. And this framework applies to not only optimal control problems and reinforcement learning with finite dimensional state spaces, but also with infinite dimensional state spaces like the shape problem. Because in the shape problem, you can move actions, you can change any point on your shape, and the shape being, say, in whatever dimension you are. And so that's an infinite number of states and also an infinite different actions you can make. And so to do this is the main motivation. Phase two is an additional phase we added to do some extra filtration of these Hamiltonian coordinates, because as you'll see, we are not given the adjoint state till you actually complete the entire path. So to build the adjoint variables into the initial condition becomes necessary to also apply some filtration. I've kind of already spoken about this. The Pontryagin maximum principle, reduces it to this symplectic ODE form, learning a vector field now in terms of P and Q on a symplectic manifold. The only difference is that instead of working with a true Hamiltonian, which captures your environment, we first learn a reduced Hamiltonian, a customized Hamiltonian based on our constant training. We don't need the full Navier-Stokes for the current conditions. So if you're trying to design an airfoil for only, going in, not in a tornado, then I don't need all of the convective terms, say all of the data is streamlined. Why should I use a heavy duty full Hamiltonian? Same thing is when I'm trying to fold proteins. I don't need the full-blown quantum mechanical, molecular mechanical solvation models. That's like imposing a model. I'm going to learn the customized that is necessary for that shape. And that's the reduced Hamiltonian. It's saying, the full model is great for all conditions, but I'm only designing it for a specific task. So learning this reduced Hamiltonian dynamical system is like learning dynamics. And there are approaches which I'll talk about. The only differences for a Hamiltonian dynamical system is I'm given the initial state, Q0, but I have to learn the adjoint state as well, because I've now captured the control into my adjoint state. So my initial state and co-state become Q0 and P0. So I can't just guess P0 for Q0. So we build another network that trains to get the right P0 for Q0, and then P0 and Q0 are fed into, this Hamiltonian dynamics learning, which is our second network. So the first network, P-phi, learns a parameterization of outputting P0 for a given Q0, and of course, this is trained for a distribution of possible initial states, Q0, to learn a distribution of P0. And then samples from this distribution learn your final terminal state and co-state. And doing that process, you learn this reduced model H theta, which is capturing the second network. So in Hamiltonian net training, what we do is we train while sampling the reduced Hamiltonian net H theta. We create a replay memory consisting of 5 tuples. You need the state, the co-state, you need the U hat, F hat, and L, and I'll explain, I think in the next slide, these U hat, F hats, L are relation to the unknown dynamics F. L is, of course, the cost functional. So I should say U hat and F hat are related to the gradient of your terminal and also your your F. So you use a neural ODE or a neural SDE to sample generalized coordinates on a trajectory outputted by the reduced Hamiltonian. Then the replay memory is updated in your replay buffer for all of, by adding these tuples for all of the generalized coordinates that you're sampling, right, on the trajectory. Then you sample a batch of tuples from the replay memory and optimize HD, just in a classical learning learning the dynamics in this network, but you're learning Hamiltonian or vector fields on a symplectic manifold. So the adjoint, of course, network training gives you backpropagation. So you optimize this loss functional with respect to the terminal adjoint variable after running this through your Hamiltonian dynamics each time. And so you train to update both your Q, which is your state, and also your P. So this is what we call phase one. And this phase one is, training yields a distribution QTPT that's simpler than that of Q0, P0 as the optimal state. QT may concentrate on a few states. So what we also decide to do, this was our phase 0, we also try to apply a filtration process in phase 2. And this filtration process is using a backward variational decoder by going backwards in time to learn my initial distributions. So it's like this entire thing becomes, this is the encoder and a decoder. So you're building this latent space using this entire encoder, very much like a variational autoencoder. So to do that variational autoencoder, of course, you minimize this loss function, which is the, based on a surrogate Q, the KL divergence of these distributions, and of course your reconstruction loss, which is the true states and the predicted states. So initially, what we do is we restrict the dynamics of the unknown dynamics as a linear function of the control. Now, it's not restricting, this dynamics is nonlinear and we have to learn it. All we are saying is that we are applying linear control, very much like what is called, ILQG, iterative linear quadratic control. But here we are not forcing it to be quadratic. It can be any nonlinear F. But having linear functions control allows you to take your control as in terms of your state variables. It's not limiting. One can also do a deep version of this that embeds the control, nonlinear control into a linear space, and then you apply that in that new latent space. So that's possible too. So furthermore, we consider the case where the cost function is separable. So we broke the cost function up into the cost involved for the state change and the cost involved for the control. And we can use the kinetic energy as a control. The more energy you need, the more cost for controlling. And we want to minimize the amount of control you want to do in an optimal path that is the minimal cost. So that U hat and F hat are related to my, the state and co-state. This is the derivative of the unknown function F with respect to your control, and F hat is nothing more than the gradient of the reduced Hamiltonian. That should have been not D, but Q. And to learn the dynamics, oops, I went too fast. We use some work I've done before with my student Luke and also student Roy, Avik Roy, and Tim and Dean in the physics department of how do you learn stably dynamics. This is what you're seeing here is learning dynamics with captures the conservation laws of the system. This is a one-dimensional Schrodinger wave equation, which is learned from data. You can see that the learning is not perfect, So there's still a lot of work done needed to capture all the conservation laws accurately from the data. And this is what is another whole line of research. So we applied this to this cart pole experiment, and given time, I'm going to skip this a little bit, but you can see that the results generally tell you that, after training, you get definitely improved results. The cart poles are being balanced. In this case, the cart poles of the untrained agent collapses. And the same thing for the mountain cart, where the untrained agent, can't make its way up to the top, while the trained agents make their way up to the top very quickly. Because I want to save the last part for maybe the best part. The best part is, how do we do this in continuous settings and for infinite dimensional spaces? And here we extended our two-phase learning to infinite dimensional space phases, which is exactly required for shape optimization, even for the isoperimetric. You have to start working with what are called group spaces of allowable diffeomorphisms. Your actions become a diffeomorphism of the vector field that transforms the shape, slowly, such that these diffeomorphisms are also invertible. And these, of course, form a sub-Riemannian structure, and it's very nicely characterized also with respect to, I'd mentioned KL divergence. Of course, you could use Wasserstein and use optimal transport kind of divergences, as well as deformations and learning. So the optimal control with NeuralPMP for infinite dimensional, applies the Hamiltonian dynamics training on a truncated subspace of the infinite dimensional space and obtains an approximate optimal control solution after learning the corresponding dynamics. And this is, using this nice paper by Aguilera, Trilla, and Trove, and Eunice on shape deformation analysis from an optimal control viewpoint. And that gives us a way to apply the idea. The idea is, and this is a busy slide, but I will quickly summarize it, is whenever you're thinking of deforming a shape and you want to build an action space that would modify the shape, then the action space can be thought of as acting on the vector field that will be mapping. So you're mapping one vector field to another vector field. And this vector field, of course, lives in the tangent space or the adjoint space of your shape. So by controlling the map, which is a velocity vector field of deformations, and doing continuous time dynamics, which is the differential of these maps, one can extend our framework to continuous time. And that's what I've shown here. The cost for controlling, is following the same formulation, and the Hamiltonian is a little bit more complicated. It's based on this differential of the vector field map, where it's the inner product, and then, of course, the cost functional. So embedding this into Hamiltonian dynamics allows us to extend this to infinite dimensional control spaces. And so for our isoperimetric problem, we took this as an example. And here's some snapshots of, this is the untrained agent. Remember, the optimal shape in an isoperimetric will always have, here, by the way, white is your shape and black is your, I'm sorry, black is your, white is your shape and black is the environment or the outside. And as you can see that you've got negative curvature regions. So this is clearly not converging to an optimal shape. And if you start to look at this, all of the negative curvature regions are disappearing, and you're converging closer and closer to, by applying both procedures, you're terminating to something, a shape, which all the negative curvature regions are. And this, of course, is not done manually. This is all done by the computer learning how to modify the shape, which is making actions using maps, which are diffeomorphisms on the vector field. So to stay in time, I will conclude. And so there are many, many next steps. NeuralPMP is a continuous stochastic to study optimal control problems, but we plan to further improve with appropriate state sample efficient learning schemes. The other work is to improve it with controlled network training processes, which have hyperparameter balancing. There are hyperparameters in any neural network, especially where you want to go to advanced stochastic, like the minimum energy compliance or proteins. Assembling together. This is a model of the entry mechanism for HIV virus, very similar to the COVID virus. So I thought it might be appropriate to say one can apply these techniques for also practical impact. So not only can you define shapes, but you can optimize them. So you can optimize them over your action spaces by doing mutations, by then making sure that in the environment, they will take on the requisite shape so that they can perform their functions more effectively than what nature has produced. So with that, I'll stop and take questions. And
Okay.
thank you for your attention.
Yeah, very nice. Okay, thank you very much. Very nice.